Very good evening to one and all. This is Mrs. Mary Ratna Anita once again welcoming you back to your pharmaceutical microbiology class. The topic for today's our class is microbiological assays. So before entering into the topic, let us see what are the learning objectives of this topic and what we are going to learn in this topic. So talking about the learning objectives, by the end of this topic, the students shall be in a position to define different terms like assays, microbiological assays, biological assays, and physical and chemical assays. And also the student shall be in a position to explain how to perform these microbiological assays and what is the importance of this microbiological assays. And they shall be also in a position to interpret the results of this microbiological assays. How you interpret the qualitative and quantitative um, uh, concentration of a product from a simple or a complex material is learnt by the student by the end of this topic. Now, coming to your main topic, that is microbiological assay. Now, before learning about the microbiological assays, we have to learn what this exactly microbiological assay term means. So when you talk about this microbiological assay, we can define this microbiological assay in a very simple manner, stating as it is a qualitative or quantitative determination of any chemical compound that from a simple or complex material. And for this, you use a microorganism. So what are we saying? Microbiological assay can be defined as a quantitative or a qualitative determination of what? Of a chemical substance. From where? From simple or complex material. By using what? By using a microorganism. So microbiological assay is a quantitative or a qualitative determination of chemical compound from simple or complex material using a microorganism is known as microbiological assay. It's a simple and easiest definition. And when you talk about the microbiological assays, so we can say this generally the assays are required for antimicrobial agents in order to find out their potency, in order to find out their pharmacokinetics, and also to have a and also to monitor and control the therapy, like clinical therapy. We need to have this not only micro assays. So when you talk about the assays, so qualitative physical and chemical assays methods can assay a clinically employed therapeutic agent. That means this qualitative physical and chemical assay methods can determine the quantity or quality of a therapeutic agent. But some of the therapeutic agents have the capability or capacity to inhibit the growth of microorganisms like your antibiotics, and some has the capacity of supporting the growth of microorganisms like your vitamins and amino acids. So these kind of agents should be assayed by using your microbiological assays. Now, when you're talking about microbiological assays are relatively as accurate as chemical methods. These are simple, these are specific, these are inexpensive. At the same time, they're convenient method to carry out. And compared with the biological assays, these microbiological assays have certain advantages. They can be performed in lesser space. Time required to perform these microbiological assays is less, and the labor required is less, and the material required is less. So when compared to biological assays, these microbiological assays are more advantageous. And as we said that these microbiological assays are very useful in detecting the changes in the potency of the antibiotic. So these are the advantages. As we said, since there are advantages, definitely there would be disadvantages also. So when you talk about the disadvantages, these microbiological assays are not as easy to perform as you perform your physical and chemical assays. Apart from that, they also are subjected to greater error possibilities. And because of these reasons, generally, whenever there is no alternative physical or chemical assay method to perform, then only we go for your microbiological assays. So these are the drawbacks of your microbiological assays. Now, talking about the main topic, microbiological assay of antibiotic. Now, when you're talking about the microbiological assay of antibiotic, we can say, so inhibition of, so here what we are trying to do, we are trying to demonstrate the therapeutic activity of a drug or an antibiotic by using standard conditions. So we are trying to inhibit the growth of microorganisms under standard conditions. These conditions are utilized to demonstrate the therapeutic efficacy of a drug. It can be an antibiotic. Since we are talking about antibiotics, it is antibiotic. Now here when we so this is generally what is your antibacterial microbiological assay of antibiotics. So when you talk generally here, the how you perform the assay means here these are nothing but comparative studies. Here in microbiological assays of antibiotics, what you do, you take a standard solution of antibiotic whose standards are already fixed, already determined. Precise standard antibiotic solution is taken according to the standards, according to different standards like Indian Pharmacopoeia or British Pharmacopoeia, different standards it is taken, and then you prepare your concentration of the solution that has to be, solution of an antibiotic which has to be tested, and this is compared with that. So it is a comparative study. And the medias which are generally used for this assays of antibiotics are, so this is the composition of the media. You have peptone, you have yeast extract. The composition of the medias are, you have peptonate, yeast extract, beef extract, pancreatic digestive casein, dextrose, you have agar, you have glycerin, polysorbate 80, sodium chloride, dipotassium hydrogen phosphate, potassium dihydrogen phosphate. So pH is adjusted. So these ingredients are taken in suitable solvents, and generally they are mixed in suitable solvents, and their pH is adjusted according to the requirements and according to the standards, and they're adjusted by using, the pH is adjusted by using 1 molar either HCl or the sodium hydroxide, and then you use this medium to perform your assay. Now, talking about the preparation of standard solution. So, in order to perform the assay, you need a standard solution, you need a test solution, you need to have a procedure. You need to have an inoculum and then a test procedure. So, talking about the standard solution, what is standard solution? Standard solution, the name itself says it is standard. It has an authentic value. So, it is nothing but authentic sample of appropriate antibiotic for which the potency has been already precised, already determined, and it is precisely determined by referring to the appropriate international standards. So the potency, the value, the efficiency, the concentration, everything is determined according to the standard, international standards. So that is nothing but the solution whose concentration is already known according and already made according to the standards of international, according to international standards, is called as your standard solution, which is used for your assay of antibiotics. Then how you prepare is, you have to take the specified quantity of antibiotic and it has to be dissolved in specified specific solvent. Then the solution is diluted to get the required concentration as per the international standard. How you're preparing your standard solution, that is the procedure. So you take antibiotic of specified standard, dissolve it in specific solvent, and then the solution is diluted to get the required concentration. So it can be a concentrated one, it can be a diluted one. So in order to make it up, it has to be made up to the required concentration as per the international standards. And whenever you perform your microbiological assays, 5 or more dilutions of this stock solution has to be prepared. So these are some of the stock solutions generally we use for, these are some of the antibiotics and the methods which we follow, and stock solvents what we use. So for amikacin, generally we follow method B, and the initial solvent is water, and final concentration of the standard stock solution is 1 mg per ml, and final diluent for test dilution is water, and median dosage is 10 micrograms. So this is how, these are the examples of some of the examples of your antibiotics like amikacin, amphotericin, bacitracin, bleomycin, capreomycin, erythromycin, famotidine. These are some of the antibiotics, and these are some of the examples of your solvents and final concentrations and median concentrations which we make for your standard solutions. Now talking about the buffer solution. How you make this buffer solution? Again, buffer solutions are required in order to maintain the pH. So how buffer solutions are made? So required quantities are taken, whatever the quantities. Generally, buffer solutions of dipotassium hydrogen phosphate and potassium dihydrogen phosphate are made, and they are up to, they're mixed in 1000 ml of water, and pH is adjusted with 8 molar phosphoric acid or 10 molar potassium hydroxide. So this is how you make your buffer solutions in order to maintain the pH. Talking about the test organisms. So these are some of the test organisms which we generally follow in order to and carry out your microbiological assays of antibiotics. So for example, for amikacin, the test organism what we use is Staphylococcus aureus, and this ATCC is American type culture collection. So they, according to the standards, they give certain numbers. So this is ATCC is American type culture collection number, and 29737 is the American type culture number for Staphylococcus aureus, which is used for amikacin. So this is how you have different organisms for different antibiotics, like amphotericin B, you have Saccharomyces cerevisiae, and bacitracin, you have Micrococcus luteus, bleomycin, Mycobacterium smegmatis, and erythromycin, you have Cochuria rhizophila, and Framycin, you have Bacillus fumilis. So these are the different organisms which are used. So I don't say this is the only thing. So different antibiotics are available and different organisms. So these are some examples of some of the organisms which are used. Now, before learning about the methods of assay, we need to know how the inoculum organisms are prepared for running your microbiological assays. So generally what you do is here, you have to maintain the test organism in the slant of method of media A. And this slant is maintained, and generally the organism is transferred to fresh slant every week. After this, what you have to do, you have to maintain the slants at specified temperature for 24 hours. Then using 3 ml of saline solution, you have to wash the microorganism with from the agar slant, and it has to be transferred onto the larger surface area of the agar. That is generally in rocks bottle, you have to take 250 ml of the agar, and you have to add this organism there. Then you have to incubate the rocks bottle for 24 hours and at the appropriate temperature. Then you have to wash the organism with 50 ml of saline solution and store the test organism, and then under refrigeration you have to wash it and store it under refrigeration, and you have to determine the dilution factor for the microorganism, and so that is one procedure. Second procedure is same, that you have to maintain the organism on the slant, and every week you have to subculturate. Then after you add it to the rocks bottle, in first method we are incubating it when we are incubating it for 24 hours, whereas here we have to incubate it for 5 days. After that, what you have to do is you have to perform the centrifugation process, and you have to separate the supernatant liquid, decant the supernatant liquid, and the concentrated for suspension is taken. It is suspended into fresh 50 to 70 ml of saline solution. And then again, you have to heat the solution at 30 minutes for 70 degrees. And then again, you have to transfer it into fresh solution. And this procedure is repeated, like heating is repeated. You have to transfer it. Then after final thing, you have to wash it for 3 times with 50 to 70 ml of water, suitable solution, and then you have to store it under refrigeration. So this is one of the procedures. So this is how you generally. So what we are doing, you're taking the organism, keep it in the slant and store it. And every week you're changing the slant. Fresh slant is taken and organism is transferred. After that, when you require it, what you have to do, you have to suspend the organism, maintain the organism at suitable temperature for 24 hours, then wash the organism with 50 ml of 3 ml of saline solution, and then transfer the organism onto the rocks bottle containing the larger surface area of the agar medium. And here this rocks bottle is incubated for 24 hours, and after incubation you have to wash the organism with 50 ml of water, and then 50 ml of saline solution, and then store it under refrigeration, and dilution factor is determined. And second procedure, same as above, but after rocks bottle, addition to the rocks bottle, you have to incubate it for 5 days, wash the solution, wash the what you're doing with 50 ml of saline solution, and then you have to heat it for 30 minutes at 70 degrees. Again, wash the spore solution with 3 times with saline solution, and again you have to heat the stock solution. So procedure is repeated, and after sufficient heatings and stocking, you have to separate the solution, test organism, and store it under refrigeration. This is how you have to prepare your inoculum. Now talking about the assay method. Main assay method, generally microbiological assays of antibiotics are carried out in two ways. One is cup plate or cylinder plate method, and second one is turbidometric or tube assay method. So cup plate or cylinder plate and turbidometric or tube assay method. Now talking about the first method, that is cup plate method A, cup plate or cylinder plate method. So when you talk about the couplet method, this method generally depends on the diffusion of antibiotic from a vertical cavity or column cylinder through the solid agar layer in a Petri plate. So vertically you make a cylinder or a cavity or a column, and then you try to put your solution, and then try to see how much it gets diffused. So based on this, we try to perform. So the growth of the test organism is generally inhibited in a circular zone of inhibition. So wherever you perform the cavity and wherever you put the your antibiotic, surrounding that area, if the antibiotic is effective, we will see how much, to what distance the organisms cannot grow because of the effect of the antibiotic. So this zone of inhibition is measured, and you have to plot a graph. So that is the basic principle of your couplet method. Now, how you perform this couplet technique is, first you have to take the liquid medium, add the suspension to it, and this inoculated medium is immediately poured onto a sterilized Petri plate or pre-prepared agar medium. And then whatever the test medium, liquid medium you have poured it onto the pre-prepared agar medium, you have to use a spread plate technique and spread the organism on the surface of the medium. Then you have to make pits or cylinders or cavities in the solid media. Then after that, what you have to take? You have to take antibiotic of standard concentration and test solution. So you have to take antibiotic, both standard antibiotic and test antibiotic, and you have to make these solutions of these antibiotic to a known concentration and appropriate known solution. Then what you have to do, then these solutions are added into the cavities or pits or wells, whatever you have digged in the solid agar medium, and into the solid agar medium. And you have to note that here, when you're filling the cavities, first thing, the cavities has to be completely filled, and the quantity what you're adding should be uniform. Like you're adding 1 ml of the standard and 2 ml of the test. No, when you're filling the pit, both has to be filled with uniform quantity. At the same time, the quantity should be sufficient enough to fill the pit completely or fill the cavity completely. Then the plates are left for standing for 1 to 2 hours in order to in order to avoid the variations due to this time interval difference. For example, you made 10 pits in that, and you are adding standard solution 5 pits and test solution in 5 pits. So what you're doing, first you'll add in the first pit, second pit, third pit, fourth pit, or fourth well. Then by the time you add to the 10th well, there would be a time gap. So in order to avoid these variations in the time between the application of different solutions, you're just leaving it for 1 to 2 hours as a pre-incubation period. Generally, either 1 to 2 hours at 4 degrees, you maintain it. And then all plates are incubated at 18 to 24 hours at a specified temperature. Then after that, you have to take out the plates, check for the zone of inhibition where the growth is not allowed due to the activity of this antibiotic. And then after that, you have to plot a graph taking your zone of diameter to the logarithm of concentration of antibiotic, and the unknown concentration is found out. So this is how you have to plot a graph. Diameter of zone of inhibition. So this would be the values of what you have taken from the, what you have measured from the zone of inhibition, and concentration of log concentration of the antibiotic in units per ml. Then plot a graph. Then you can get the concentration of unknown sample solution. So this is how you perform your antibiotic. So what you're doing, you are taking the liquid medium, adding the test organism, and then you are pouring this liquid medium onto the Petri plate, sterile Petri plate, and spreading the organism on the surface. Then after that, once it is solidified, then you are making wells in that. So wells means you're making small holes or digging small holes in that. Then after that, what you're doing, you're taking antibiotic of standard and test. Whatever the antibiotic you have to test for, you have to perform the assay, as well as standard antibiotic are taken, and concentrations are made to appropriate solutions. appropriate solutions are made to known concentrations. Then these concentrated solutions are added to these wells what you have made in the solid agar medium. Then here we have to make sure that the quantity should be uniform, and the whatever the quantity is added, it should fill the pit completely. Then incubated for 1 to 2 hours in order to avoid the variation because of the time gap in filling the different solutions. Then after that, you have to incubate it for 24 hours, or incubate it for almost 18 to 24 hours. And then after incubation, take out the plate, check for the zone of inhibition, measure it, then plot a graph taking the diameter of the zone of inhibition as, against log concentration of your antibiotic, plot it, and the interpolation will give you the concentration of the test sample. So that is how you perform your test for antibiotic by cup plate method. Then next one is turbidometric method or tube assay method. So generally this method depends on the growth of microbial culture in uniform solution of antibiotic in a fluid medium that is favorable for its rapid growth without the antibiotic, in the absence of antibiotic. So whatever the medium which supports its growth, if at all antibiotic is not there, the medium that can support the growth of organism is taken, and you perform the assay method. So this method has an advantage of shorter incubation time when compared to your couplet, where there you have to incubate it for 24 hours, whereas in turbidometric method, you can incubate it only for 4 to 5 hours. And this method is not recommended for cloudy or turbid preparation, because turbidity can confuse you about the growth or colony formation. Now, how you perform here means you have to take 5 different concentration of the standard solutions, and by diluting it with the stock solution that is prepared. Then the median concentration of the standard solutions has to be taken, and then according to this median concentration, you have to make your test solution. So 1 ml of each of standard and test solutions are added to test tubes in duplicate. That means 1 ml has to be added in 2 test tubes, 1 ml of standard and 1 ml of test. That is your primary step. Then at the same time, what you have to make control tubes, like taking 3 tubes again. In 1 tube, you have to add inoculated culture medium, that is culture medium containing organism. Second one, you have to add inoculated culture medium which is immediately treated with 0.5 ml of dilute formaldehyde. And then the third one, which contain the culture medium but not the organism, uninoculated culture medium has to be taken. So these 3 are taken as blanks or controls. So what you're doing, you're preparing 5 concentration of the standard stock solution. From that, you're taking the median concentration. According to that concentration, you're making your test solution, and then 1 ml of each standard and test is taken in duplicates. That is 4 test tubes you have 4 test tubes now, and along with these 4 test tubes, you have to make 3 more controls. That is 1 containing the inoculated culture medium, that is organism with culture medium, and then second one, organism with culture medium, which is immediately treated with 0.5 ml of formaldehyde. And then third one, without organism, you have to take the culture medium. Then all the 7 tubes are incubated for a specified temperature for 4 to 5 hours. Then after incubation, 0.5 ml of formaldehyde, dilute formaldehyde is added to all the tubes. Then the growth of the test is measured by determining the absorbance at 530 nanometers for each of the solution in the test tube against the blank. So you have to absorb the test, take the absorbance, and then plot a graph taking absorbance according to the against the concentration. So that will give you your concentration of the required one. So that is about your turbidometric method. Now talking about your microbiological assays of your vitamins. When you talk about vitamins, we know that when we were learning about the nutritional requirements of organism, we learned that vitamins are one of the major requirements for the growth and development of the microorganisms. So it is the ability of these test organisms to synthesize these factors which are being assayed that form the basis of this microbiological assays of vitamins or amino acids. So talking about the microbiological assays of vitamins, some of the test organisms used for assaying the water-soluble water-soluble vitamins are, so you can see vitamin B12, the test organism is Lactobacillus leishmaniae, and the incubation temperature is 37 degrees and pH has to be maintained in 6.1. And vitamin B6, Saccharomyces urarium, and 30 incubation temperature, and 4.5 is your SAPH. Riboflavin, Lactobacillus casei, and 37, 6.8. Thiamine, Lactobacillus viridensys, and 30 is your temperature and 6 is your pH. So these are the standards generally we maintain. Now, talking about the microbiological assays of cyanocobalamin. Generally, the microbiological assays for amino acids and vitamins are same. The methodology is same. So, for our convenience, we take cyanocobalamin or B12, vitamin B12 as an example. Now, this vitamin B12 assay is performed by using two methods again, titrometric method and turbidimetric method. So, talking about the titrometric method. So before talking about the titrometric method, how you have to make your test solution, or you have to make your inoculum, let's see. So first, test solution, how you make, you have to take the accurate amount of the material that is to be assayed and dissolved in water or suitable diluent. And then pH has to be maintained by adding either HCl or sodium hydroxide and to 6. And then the final volume is made up to water. That is your, how you make your test solution. Then preparation of the inoculum. How you prepare the inoculum? Generally, few cells of Lactobacillus leishmani are taken from recent subculture and they are transferred to 2 sterile tubes, each containing 10 ml of the culture medium. So 2 tubes has to be taken. In each tube, you have to add 10 ml of culture medium, and to that you have to add your few cells of your organism. Then the tubes are incubated at 18 to 24 degrees for 18 to 24 hours at 37 degrees. Then after incubation, the culture tubes are centrifuged and the supernatant liquid is decanted, and you have to take this suspension. And this suspension is transferred into a, again, fresh sterile 10 ml suspension. Then again you have to incubate it, and again you have to centrifuge it. In this way you have to repeat the process for 3 to 4 times, and finally what inoculum contains is 1 ml of the suspension of the cells are aseptically transferred into 10 ml of the stock solution, and then the resulting suspension is considered as inoculum, which is used for the carrying out your assay procedure. Now, talking about the titrometric method. Now, when you talk about the procedure of titrometric method, here generally the test tubes, here 10 test tubes are properly taken, and 10 test tubes are properly, you have to take 10 test tubes properly cleaned, then sterilized, and then to this 10 test tubes, each test tube you have to add 0 ml, 0.5 ml, 1 ml, 2 ml, 3, 1.5. In that way, you have to keep increasing 0.5 ml till 5 ml. You have to add standard soluble solution to each of the test tube. And to each of these test tubes, again, you have to add 5 ml of basal stock solution or basal media solution. And then the final volume is made up to 10 ml using water. For example, in the first test tube, you'll be adding 0 ml of standard stock solution. That means you have to add 5 ml of basal medium and 5 ml of the water in order to make it to 10 ml. Then in the second test tube, you'll be adding 0.5. So you have to add 5 ml of basal solution and 4.5 ml of water. So in this way, you have to keep increasing, adding your, the final volume should be made up to 10 ml with water. Then 4 more test tubes have to be taken, sterilized test tubes have to be taken, and then you have to add 1 ml, 2 ml, 3 ml and 4 ml of your test solution to be assayed. And then all the test tubes are sterilized by autoclaving procedure at 121 degrees for 15 to 20 minutes. And then after that, the tubes are allowed to cool down. And once the temperature comes to room temperature, then these test tubes, all the test tubes are to be inoculated with 1 drop of inoculum. And inoculum, we have made inoculum solution that is containing the cells of Lactobacillus leishmani. Then all the tubes were incubated for 64 to 72 hours at a suitable temperature within the range of 30 to 37 degrees. Then the contents of each tube are titrated with 0.5 normal sodium hydroxide or using 1% weight by volume bromothymol blue as an indicator. Then the average titration values are to be taken for each level of standard as well as test samples. And then you have to plot a graph taking average titration versus the standard levels of standard cyanocobalamin solution, and the concentration of unknown sample can be determined. So that is the procedure what you follow in titrometric method. And how you make your standard solution, cyanocobalt solution means it should contain concentration that 1.1 micrograms per ml in 25% alcohol will give you standard solution. And this, whatever the stock solution, standard stock solution you're making, it has to be refrigerated and it cannot be used for more than 2 months. Then talking about the basal stock solution, what you added, 5 ml of basal stock solution in each test tube you have added. This is the composition of your basal stock solution, which contains all these ingredients: L-cysteine, tryptophan, HCl, adenine guanine, uracil solution, xanthan solution, riboflavin, thiamine, biotin, nicotinic acid solution, p-amino benzoic acid, pyroxidine, pyroxole, pyroxidamine solution, pyridoxamine solution, calcium pentothenate, folic acid solution, salt A solution, salt B solution, asparagine solution, acid hydrolyzed casein solution, dextrose, sodium acetate, ascorbic acid, and sorbitol monoacetate oleate derivatives. All these are included to make your basal stock solution. Then we have already discussed how we make your test solutions and inoculum. Then turbidimetric. This turbidimetric method is similar to that of your titrometric method. The only difference here is, here in this we need to take 2 more test tubes and included, in which neither standard cyanocobalamin solution is added, nor test solution added, nor inoculum is added. You just need to add your basal stock solution and water. And all the test tubes are incubated at 30 to 37 degrees for 16 to 72 hours, 16 to 24 hours. And then by using an uninoculated blank solution, you have to adjust the transmittance to 640. And then each tube is thoroughly mixed and transmittance is recorded. Then you have to plot a graph taking transmittance versus against corresponding levels of standard cyanocobalamin solution. So when you plot a graph, you can get the standard concentrations. So this is how you determine your concentration of vitamin B by turbidimetric method. So these are the methods in which we follow in order to perform the microbiological assays of antibiotics, vitamins, and amino acids. And you can get this topic from NK Jain or Pharmaceutical Microbiology by Vallabh Prakashan. And even in internet also, there's a lot of information. So if you have any doubts, feel free to ask me anytime, anywhere. You can text me, message me. And with this, we have completed this topic. Let's meet with a new topic in the next class. Thank you.